Hi everyone, I'm Dave Reimann. I'm a professor of math and computer science at Albion College, and I'm going to be talking a little bit about reciprocal polyhedral forms using strip pairs as a part of the Bridges 2020 conference. So this work builds on work that I've done for the last few years involving constructing objects starting with a polyhedron and replacing the edges in that polyhedron with some kind of square or two-dimensional piece of some kind. Here I'm holding a roughly spherical object where I've replaced the edges of an icosidodecahedron with these Bridges 2020 postcards. So to explain this process in a little more detail, I want to start with these Platonic solids and talk about how that process is carried out. So if I look at this dodecahedron here and replace the edge in that with a square and do that for every other edge, I end up with a form that looks something like this. Now these squares are made from paper-backed bamboo veneer. They have some flexibility that allows them to stretch and expand. You wouldn't think that replacing the edge with a square would allow that form to connect nicely, but because of the flexibility in the material, that does happen. And if we look at these, it's kind of interesting that when I look at, say, a face of the underlying polyhedral form, so this pentagonal face here, what happens in this process is that becomes an opening space here. Similarly, each vertex in this underlying polyhedron becomes an opening in this polyhedral form. Similarly, that process, because each vertex is mapped to an opening, each face is matched to an opening, polyhedra that are duals of one another end up with forms that are very similar. Here, the difference between, say, the dodecahedron and the icosahedral form is that the bending is due to the properties of the material. This has a preferential bending angle where it's real stiff in one direction, sort of along the axis of an edge, and then flexible along the other direction. That gives these forms sort of a reminiscent feel to the underlying polyhedral form. So, for example, in the octahedron, we see this square opening corresponding to a vertex, whereas in this example here, the square opening corresponds to the square face of that cube. Tetrahedron is self-dual, so it looks the same. The other thing is that this can be done where the opposite diagonals of these edges are both so the same polarity, I would say. So either they're both over or they're both under. And as we get to a face or a vertex, we can construct those where this square is over this one, 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 and so on. Now, I've done a number of artworks related to this. This one is called Inconceivable Symmetries from 2014. It's based on the Rhombic icosidodecahedron, and it's made from 120 pairs of packaged prophylactics. This one is called Sierpinski tetrahedron. It's made from 258 playing cards. This one, Globe Flowers, we did at Family Day in Bridges in 2016. Capsule, I did in 2016. It's essentially a cylinder that's made with a hexagonal tessellation of the plane rolled up, and then two dodecahedral caps. The replacement of the edges doesn't necessarily have to be a square. In this case, we see that this particular unit is a rhombus, and so you can get some interesting forms by replacing the edges with rhombic tiles. This is part of a continuum that starting with some kind of underlying polyhedral form, we can replace the edge with a square. That square can be sheared. We can continue that shearing process, clipping off the corners here into a situation where that in the limit it becomes just a strip, and that strip still has 4 connection points, just like the 4 corners of the square, except that these opposite corners have been either shifted to the outside or to the inside, and so the polarity of the endpoints is the same, and the polarity of the interior points is the same, but the opposite of what they are for the endpoints. So here's some examples with that. So starting with squares, we can shear those into rhombic pieces, and then those can become long parallelograms, and eventually we can think about those as strips, what we see here on the right-hand side, similar to what we see here with the icosahedron. And we're not limited to using just squares or parallelograms or strips. We can actually use more interesting shapes. For example, this snake shape. I can think about it having these 4 points lying on the corners of a parallelogram, and then using the same kind of connection process as we did before. Or I could think about this as being a strip that has just been deformed slightly. Again, this point here and this point here are opposite corners on this parallelogram, and so they're going to have the same polarity, as well as these 2 interior points are going to have the same polarity, but the polarity of these is going to be opposite of these endpoints. So that's what we see here in this work, 60 sinusoidal serpents slithering on a sphere, where if I look at this particular snake here, the snake at its endpoints is over this snakes that it's connecting to, whereas in the interior, the 2 connection points, the snakes that attach are on top of that snake. Now this kind of reciprocal process where we have this kind of weaving of these strips is related to work that was done by Rinus Roelofs at Bridges 2003 and others since then. But we can see kind of an example of that here, where I have this ruler where it's just lying flat in the plane. The endpoints are over the rulers that it attaches to, and then the rulers attaching in the middle are on top of this ruler. So this ruler is kind of an over, under, over pattern that we see here. This is related to work that, as Rinus Roelofs has pointed out, is related to work that's been done by Leonardo da Vinci 500 years ago. So this is a picture from his Codex Atlanticus notebook, and what we see here is several drawings of reciprocal structures. If we look carefully at this one, it's slightly different than that figure I just showed with rulers. If we look at this figure with the rulers, if I just look at this ruler here, what we notice is that in the interior, these connections are made from opposite directions. So this is coming from below, this is coming from above. Whereas in this particular figure here, we can see that along this particular edge here, both of the connecting pieces are coming from the top. Whereas here, both of the connecting pieces are coming from the bottom. And we see that in every particular place here, that along any one of these edges, any one of these struts that we see here, these strips, we see that the connections on the interior are coming from the same direction. We never have that kind of opposite connection that we saw with the rulers. Now, I was trying to come up with a way of thinking about this from the standpoint of this sort of shearing and expanding process. But I think it's helpful to think about this from a different standpoint when we look at these reciprocal structures. So one way to think about these reciprocal structures is I can start with some kind of grid like this. I can then sort of slightly kind of pinwheel out these edges where they still remain either vertical or horizontal, but they're just shifted around that vertex slightly. So as we keep doing that, that vertex becomes an opening, and that opening gets larger and larger. And here in this final picture that we see on the right, what we have is that for a particular edge, we have 4 equally spaced connection points, one on each end, and then 2 intermediate points. And in here, the connections are made from opposite directions. Another way we can think about this is that if I think about this underlying tessellation, I can really think about this edge as really being 2 pieces that are just connected, stuck together here. And in this sort of pinwheeling process, not only are we pinwheeling away from this vertex here, but we're also moving each one of those edges further and further and further apart. So this edge that we see here is in some sense being split, and we end up with, rather than just one edge, we end up with a pair of edges. So if I think about this pair of edges here, we see that I have a pair of edges coming in from one side and a pair of edges coming in from another side. But in this limit here, we see that again each one of these struts has 4 connection points, one on each end, and then 2 intermediate. And those intermediate ones have connections coming from the same direction. So this gives us a way of starting with some kind of reciprocal structure like this, and then just splitting each one of these edges into 2, split that edge along its long axis, split it into 2, and then we can end up with a form that looks like this. And this really matches what we see in Da Vinci's Notebook and other constructions by Rinus Roelofs. So here I want to use this technique to show some new structures based on some simple polyhedral forms. So what we have here is the tetrahedral form using strips, and then so this is the simple reciprocal structure, and then what we see here is this the paired strip reciprocal structure. So if I look at an edge here, that edge has connections from opposite sides on these interior points. Whereas here, with this one, if I look at this edge, the connections are both coming from the same direction in this case. Similarly, I can look at any particular edge and I can find its pair. So right now I see this edge is paired with, or this strip here is paired with this strip here. This strip here is paired with this strip here, and so on. We have another example based on the octahedron and cube. And so here we have the octahedral form, we have the cube form. And if we apply this process, we end up regardless of which one of these we start with, we end up with this structure that we have here. So this is kind of interesting in the sense that what we end up with is kind of a dueling process where, because the octahedron and the cube are duals of one another, they generate this same form. So I can see this particular square here maps to, say, this square here. This triangle here maps to this triangle here. And this triangle here maps to that triangle. This square maps to this square. Because of this process, what we see is that the underlying vertex, regardless of which one of these objects I'm using, maps to a small polygon. So it's the smallest form that we can make with these, so in this case, 4 strips coming together. And then same with the faces. Each one of these is kind of the smallest. So note that here I don't have any intermediate connections in this triangle or in this square, whereas in here there is one intermediate connection point along this the edges of this triangular opening here. Again, we can also see the fact that this strip here has a pair that's here. The connections to this strip are coming from the lower right here, and the connections to this strip are coming from the opposite directions up here. So similar process for the dodecahedron and the icosahedron. So we end up with this elegant form here in the center. And then we can apply this to Archimedean solids. So this is the truncated tetrahedron. This is the paired strip reciprocal structure corresponding to that. Here we have the cube octahedron and the paired strip reciprocal structure here. And this is similar for the icosidodecahedron. So we have the icosidodecahedron at this point, and then this paired strip reciprocal structure here. So one thing to note about this one is that that there are some bumping outs that we see. This particular strip here is fairly flat, whereas its pair sort of bends and twists quite a bit. And that gives this some rather interesting characteristics. I can replace, so starting with this polyhedral form here, I can replace each one of those strips with a snake motif, as I showed earlier. And so this snake motif ends up having paired snakes. So this snake that's here pairs up with the snake that's here. And note that the head, the snake is crawling to the upper right, whereas over here this snake is crawling to the lower left. So these snakes are going in the opposite direction, and that's true of every pair of snakes. So if I look at this pair of snakes here, this one is going down, this one is going up, and so on. So that's a fun thing about this kind of construction, is that we can use an asymmetric motif like these snakes and have them kind of pair up so that that unit becomes more of a symmetrical unit, that unit being a pair of snakes. So anyway, in this work we've talked about a framework for conceptualizing a large class of reciprocal structures, and that framework allows us to transform one class of reciprocal structures into a larger structure using this splitting process. We need to use flexible units in many cases. However, it seems reasonable that if we're interested in structures with less curvature, we might be able to achieve that by varying the length of individual units or changing the positions of holes in those units. An interesting feature of paired reciprocal structures is that each strip in the pair can be associated with a half edge of the original polyhedron. So I appreciate you listening, and looking forward to any comments or suggestions or questions that you have about this material. Thank you very much.